So super big important points here today. You'll hear me kind of emphasizing a little bit of, on the loud side here in a little bit, because people ignore me on this kind of stuff. And so logarithms, they mean exponents. So don't get all hung up and think, oh, this is some kind of strange thing. You know what exponents are. So when we talk about a logarithm, all we're talking about is an exponent. Now, I gave the example in class. If it's 27 degrees out and we go outside and the temperature goes to 29 degrees, it goes up 2 degrees, are we going to notice a difference in the temperature? Probably not. 2 degrees temperature change is not a big noticeable change. But that's because it's a linear scale, and going up by 2 degrees is not drastically different. But when it's an exponential scale, when it's going up by multiplication, like these are powers. These are not, based upon this statement right here. So the size of an earthquake, the Richter scale, tells me how big the earthquake is. Would I notice the difference between a 2 and a 3 or a 2 and a 4? Well, look at the magnitude of the power, and we're jumping up by a lot. And so, yes, if something is 10 times larger, I think I'm going to notice. I mean, if the temperature outside was multiplied by 10 and we went from 27 degrees to 270 degrees, I think I would notice. Would probably be gone as well, but it's beside the point, evidently. So, logarithms, are they different from what we've talked about before? Like, we all know how to take 2x equals 8 and solve, right? You divide by 2. You do what's called the inverse operation. But at this moment, how do I handle this? Because I don't know what the inverse operation of that is. Well, before we get into that, could we handle it a different way? Could I rewrite 8 as a power of 2? And the answer is yes, I could write it as a power of a 2. And then what if I said write an exponents only equation? And what do I mean by an exponents only equation? Well, that means this exponent is equal to this exponent. I mean, you can clearly see that the left side and the right side are exactly the same, and the bases are identical. So an exponents only equation would be simple, and it's already solved for. We might in the future have questions like 2 to the 5x plus 7 equals 2 to the third. And if we're writing an exponents only equation in that situation, we would take this, set it equal to that, and we would keep going from there. But in this case, when we set the exponents equal to each other, we were literally finished. So the inverse of exponentiation is called a logarithm, okay? And we need to get good at understanding and going back and forth between these two things, which at this moment you are not good at. So, but you will be in a little bit. Okay. If you don't get what we're about to do, this becomes a really difficult section. All right. So we need to get really good at changing back and forth between things in terms of logarithms. Now, before I get to that, I'm going to ask you a question. Hold on a sec. Are these two equations that I've written at the top in purple, Are they equivalent? Yes or no? Are they equivalent? Yes, they are. Is one easier to see the value of x than the other one? Yes. But you should all know that these are equivalent statements. What we're about to do is write equivalent statements. Sometimes it is easier to use one form than another. So that I can emphasize something. Because people ignore me. That's why. For instance, what we have right here is called exponential form. And that exponential form could be an example like this. 2 to the 5th equals 32. 2 raised to the 5th power gives me 32. Now, the other form, which I need to get you, and folks, I am going to emphasize until you get good at this, I'm probably going to use boxes and have you guys fill in the boxes. And I know that you might think, okay, well, that's kind of really a kid-like thing until you get good at it. And when you get good at it, no, you don't need boxes. But it kind of gives you some guidelines as to how to write these things. For instance, we call this one the base. Of course, this one is called the exponent. And the last one has kind of a computer programming type term called the argument. And this other form right here called log form, well, it's got boxes to fill in as well. And obviously, when you get good at rewriting things in log form, you can ignore the boxes. What I have noticed is that people have a hard time writing this because sometimes their numbers or their expressions end up like way up here. And I'm like, wait a sec, why are we putting something like up in the universe somewhere? I'm like, notice that in that box, everything is at the same level except for one thing. One thing is written a little bit lower than everything else. And that right there is the base. Now, logarithm means what? What does logarithm mean? Exponent. That must mean that the other side of this has the exponent on it. Sure does. That leaves me with one box remaining, and that's this one right here, and I'm just going to abbreviate it ARG for the argument. So if I was writing this in its logarithmic form, notice what I chose first. I choose, until you get good at this, I would recommend that you start with a 2, the base. Write the base in first. Okay? So literally, that would be my first thing that I would write. But my second thing that I would write would be the exponent. I would go to the other side of the equal sign and put my exponent in. So what's your choices? Which one's the exponent, 5 or 32? In this case, it's 5, right? Well, now I only have one box left. I can't screw this up. Log base 30, log base 2 of 32 equals 5. That is the same. These are equivalent forms, folks. They are equivalent forms. Now, is one easier to use than the other? Depends on the situation that I'm in. Sometimes I'm going to say one is better than the other. If you struggle, we have got to get you to the point where you can go back and forth between these two forms. Because if you can't go back and forth between these two forms really easily, this becomes very difficult. Now, later, we will talk more about this and how this and this are what we call inverse functions of each other. Okay, we'll talk more about that later, but a logarithmic function looks very much the same. But we'll discuss more of that later. Yes.
I'll try it in one.
All right. Write the logarithmic form of y equals. All right, so let's see here. They want me to change that into log form. Okay, so log, and I'm going to have 3 boxes to fill in here. Start out with the base. What's the base? Your choices are y, 8, or x. Which one of those is the base? 8. Go to the other side where the exponent sits. Would it be x or y? Which one is the exponent? X. That leaves 1 box left. You can't screw this up, folks.
Y.
Correct. But I always recommend that you find the base first. You go to the exponent second. And then you have 1 box left. It really is, until you get good at this, use the boxes. And then when it's like training wheels, once you get good enough, take them off. Some of you need to be writing this stuff down and not just, unless you're worshiping me for a different reason. Okay, exponential form. All right, we already talked about all that. Okay. Write down the logarithmic form of this. What is the logarithmic form? So fill in the boxes. Go. Get it filled in. So base is 3, exponent is 4, 81. Log base 3 of 81 equals 4. Log means exponent. The exponent on 3, which gets me 81, is 4. What's the exponential form? Okay, so now they're asking me to go the opposite direction. I would recommend that you start with the base. What's the base? It's either 10, 1,000, or 3. Which one is it? 10. Then I would go to the exponent. It's either 1,000 or 3. 3, and that leaves me with 1 box left, 1,000. Okay, there we've got it. We've got it in its exponential form. That's it, folks. Not tons of. Now I'm gonna share something with you. This is called a common logarithm, and you will rarely ever see me write a base of 10 on a common logarithm. The more common way to see it would be log 1,000 equals 3. Now, if you can't sleep at night unless you write that little 10 in there, go for it. Every one of your calculators is programmed with base 10. But more than likely, you would see it written like this, and you would need to be able to interpret it to that right there. But if it really bothers you, then I would suggest you write in your little 10. It's okay. It's fine. It's just when we have a common logarithm, you're going to see in other problems, they will not write a base of 10. You need to know that it's base 10. Now, in other situations, yes, they write in the base because it's not base 10. So when we get back from lunch, we will continue. All right, it's working now. So we would change this to its exponential form. As you can see, let's see if I can erase some of this. You've got to be able to change from logarithmic form to exponential form. You got to look at this and say, oh, that's the base. The exponent's on the other side. Now notice I put the equals x on there because they didn't. Remember, I want the 3 boxes for you to fill in. I want you to be able to look at this and go, all right, so there's a box, oops, there's a box, there's a box, and there's a box. They go in a particular place in the exponential form. So you substitute base, exponent, that leaves 1 box left. Now, as you can see, we changed 125 into 5 to the 3rd power, and then we literally compared the exponents and said, hey, x has to be 3. Okay? If you do the same thing on the next example, you change it from its log form into its exponential form. Base 1/4, exponent is x, and then it equals 16. In this example, you have to change both sides. You can't leave the 1/4. You have to change it to 4 to the negative first. And you can't leave the 16. You got to change it to 4 squared. Therefore, now we can compare the exponents. We can multiply these two exponents together and get negative x. And the other side has a 2. So that's negative x equals 2. And you can solve it and find out that x is negative 2. Okay. On this example, if you do the same thing, the base is 3. The exponent is x, it equals 0. There is no solution to this because no matter what number you put in there for x, you are always getting a positive answer. You can never get 0, and you definitely can't get a negative number. Well, it goes along with this picture. Here's the exponential growth picture we have looked at before. The range of that goes from 0 to infinity and does not touch 0 because that's a horizontal asymptote. That's why that's a no solution situation. On this next one, when we change it to its other form, the base is 2, the exponent is x, it equals 2 to the 8th, we see right away, oh, doesn't x have to be 8? And the answer is yes, it does have to be 8. There's no other choices. Okay? So I wrote this note on the side. When the base of the log and the base of the argument match, they have just handed you the exponent. They gave it to you. Now keep in mind, remember, logarithm means exponent. Every single time we're trying to figure out what is a log is an exponent. That's why I keep, putting exp next to this thing on the other side, because that's the exponent. Logarithm means exponent. I did another example right here where, there's no way, like I just gave you an example where something to the, you can't raise something to the, to any power and get 0. Well, if you can't raise it to, any power and get 0, you ain't going to raise it to a power and get a negative number. That's just not possible. Now, there's 2 different logs that you need to be familiar with. Common log, and you can see over here on the right side of the screen, they write log x. Notice that it does not look like it has a base. That's what's called a common log, and it is a base of 10, always, 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 always. Well, there's another notation, lnx. That's not in, that's ln for natural logarithm. Okay? lnx is automatically base e. You can see here how somebody could write a subscript of e in there, but nobody ever does that. Okay? It's always lnx, and you're supposed to know. You're supposed to know that that is a base of e. Yesterday we talked about naturally, and then I wrote out natural e, just to try to get you to remember that a natural logarithm is base e. Okay, then they give me some examples where I literally am typing on a calculator. Every calculator has base e and base 10 programmed into it. So literally I typed log 900 and I got 2.9542. Obviously it goes on forever and ever, never stops and never repeats. They told me to round to the nearest 10,000. Okay, on the second part, the button that you're looking for the natural log is right on the calculator, ln. But right above it is e to the x on most calculators. If you need help with that, I can show you on yours. So when you type the ln, the next thing I need is e. And if your calculator's waiting for an exponent, and this says e, we know that's e to the first. And when you do that, you find out that you get 1. Well, didn't we just talk about a few seconds ago, if the base of the logarithm, now remember, the base of the logarithm is right here, and nobody writes it in there. That's a base of e, but nobody writes it in there, like I said. Then they gave me the answer. They gave me the exponent of 1. The last one there is also another one of those impossible situations. There is no solution. Has everything to do with the logarithm graph. And the log graph has a domain of 0 to infinity. This is the picture of a logarithm graph, and it opens up to the right. From 0 to infinity, it never crosses that vertical asymptote, so there's literally no points over here. So when you asked me to find a logarithm of a negative number, it's not possible, folks. Okay, and let's see what the last example here was that we worked on. We had a couple examples here on example 5. We changed it to its exponential or its log form first, right? So log form first. The base was 10. The exponent was x minus 1 on the other side, and that left 25. We could type this on our calculator, log 25, and get 1.398, blah, 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 blah. And then, of course, we could add 1 to get the final answer. In this case, 2.398. And this one was a natural log, and we wanted to change it back to its exponential form. So the base was e, the exponent was 4, and that left me with 2x plus 3. You can type e to the 4th on a calculator. It's going to give you this nasty long decimal. We got 54.598. And then we could do the simple things like subtract 3, divide by 2, and get the 25.8, 25.799. We did go through this example right here, which we changed it to its log form. The base is obviously e, so that's why we chose ln. The exponent on the other side is x plus 2. That leaves one box left, which was the 8. And then we can type ln 8 on a calculator. It gives me this 2.079. There's one step left to do, and I will leave that into your capable hands. I'm just testing my recording feature because I am frustrated at the moment, but hopefully it's fixed by now. So example 6, they literally want me to plug in a value. X represents joules. They give me the joules value, and then they want me to plug it in. All right. So now what? We plugged it in. We put it in that spot. What you going to do with it now? If you have something written in its exponential form and you don't know what to do with it, what form should you change it into? Log form. I'm telling you, folks, you've got to be able to go back and forth between this log form and this exponential form, and if you can't, it's going to cause a serious problem. So, figure out what goes in the boxes. What's the base? Right here, 10. What's the exponent that goes on the other side? There you go, 1.5m plus 12. That only leaves one box left, which is 4.2 times 10 to the 20th. Can you type everything on the left side of this equation? Yeah, we can just type it on a calculator, folks. So you should be doing this and solving it. Go. Getting it into that form was the toughest part of this whole problem. Okay, so when you took the logarithm of 4.2 times 10 to the 20th, hopefully you got 20.623. Was that the hardest part of this question? I mean, isn't it pretty simple from there on out?
Yes.
Right, you're just going to be subtracting 12, dividing by 1.5. Not talking over me while we're working together. You know, that kind of thing. Let the calculator do the work. Right? 20.623 minus the 12 divided by the 1.5. So we get an approximate value of 5.75. Yeah. Are you going to type a base of 10 in your calculator when it's a base 10, or is it already programmed into your calculator? It's already programmed in, folks. You're just typing log 4.2 times 10 to the 20th. Calculator knows what to do from there. I do like how easy things are on Desmos. I mean, even you know, when I just type e to the fourth, you know, it's just the letter E on the keyboard, right? I don't even have to do anything special, you know. What is? Yeah, that's true. That is true. But I like how it's displayed like this. It's not too bad on there, but um okay. This one right here? It's the same type of question. You're just plugging in a different number. You log of that thing right there? Okay, equals, and then you have the 1.5m plus 12. You're just redoing this with a different number. That's on the other side of the equal sign, right? Right? Yes, sir. 5a? You mean the one we had before? Oh, okay. What's the question? Okay. So what is your particular question? Are you asking me what step number 1 is? Does this problem, folks, when you look at this problem, do you automatically think of using E? I need to know. I need to know if you think we should use E. This right here is telling me we are not using E. Okay? Log, logarithm, but it's a common logarithm, right? So what base is that? What's the implied base? That's a 10. Now, I told you if it really bothers you and you want to put a 10 there, that's fine. Okay? But I would immediately be expecting you to change it to its other form. What's the base? 10. What's the exponent? And then it equals 3x minus 2. I'm pretty sure you know 10 squared is 100. I'm pretty sure you know how to add 2 and divide by 3. It's changing it from its log form to its exponential form that's the tricky part of that question. But I think you're good enough to do it. It's 1. 10 squared? I'm not sure that could possibly be. Is that 100 plus 2 is 102. And 102 divided by 3, I don't think that gives me a 1. Okay, but I'm looking at this. This is what I'm typing in my calculator. 10 squared. 10 squared. And that's going to give you 100. Okay. and then it's equal to 3x minus 2. So then it's just back to algebra 1 stuff. I'll let you think through that. Okay, that's probably right. Yep. Okay, and I think we're done with these 6-3 notes.